When a new engineer joins a team with a monolithic repository, hundreds of thousands of lines of code, the first challenge is figuring out where to start. Traditionally, we've relied on static analysis tools like NIP to map physical dependencies. They show exactly which module imports which library, but provide zero context on the underlying business logic or the operational role of those files. The result is a topological map so dense, developers call it a hairball. Ramp-up times stretch into months, initial code contributions carry high defect rates, and senior engineering resources are drained by constant manual mentorship. To solve this, a tool called Understand Anything, built by developer Lum110, proposes a different approach. Prioritize teaching the codebase over simply drawing it. It attempts to provide persona-adaptive abstraction rather than raw structural data. Effectively, the project moves the challenge from mapping file structures to translating raw technical syntax into a plain English pedagogical narrative. This table outlines a binary dilemma. Static analyzers provide structure but lack context. Conversely, AI models extract meaning but miss dependencies and hallucinate inheritance. Understand Anything harmonizes deterministic preprocessing with AI, achieving both dependency mapping and logic extraction. The stated ambition is to operationalize docs as code, treating high-level architectural documentation as a version-controlled asset that is systematically updated alongside executable binaries. While this hybrid engine theoretically bridges the gap between structure and semantics, its actual implementation reveals the rigid economic and security boundaries of modern agentic tooling. To understand how this architecture operates, we look at the first phase of its pipeline. The system bypasses large language models in favor of a strictly deterministic scan using TreeSitter. TreeSitter is a high-performance parsing library. It reads the raw source code across more than 10 supported languages to extract irrefutable facts, hard file dependencies, object inheritance chains, and exact call sites. These mathematically precise relationships are compiled into a universally accessible data structure known as the import map. This import map establishes an unshakable topological ground truth, and it explicitly offloads the process of deriving basic structural connections from the downstream AI agents. By pre-computing the structural math deterministically, the architecture protects expensive, limited AI context windows, reserving LLM compute for high-order semantic reasoning tasks. Once that deterministic truth is established, the probabilistic layer takes over. The import map is fed into a highly orchestrated, 7-stage multi-agent LLM pipeline. It starts at the micro level. Multiple file analyzer agents run in parallel, processing batches of 20 to 30 files to extract semantic functions and the specific purposes of individual classes. Next, macro-level agents synthesize that data. An architecture analyzer categorizes these components into vertical layers, like API or service, while a domain analyzer extracts horizontal business workflows. Before finalizing the result, a graph reviewer agent steps in as a programmatic quality assurance measure. It executes referential integrity checks to ensure no orphaned nodes exist in the final JSON output. This diagram illustrates how the multi-agent output maps to the user interface. A single analysis engine projects the data into 3 distinct views: business flows for managers, concept explanations for juniors, and deep dependencies for senior architects. Developers interact with this projected data through a locally hosted web dashboard, built with React and served via the Vite build tool. But here we hit the first layer of operational friction. The dashboard defaults to binding to the local IP address on port 5173. Because this is the default for most modern front-end frameworks, developers often experience silent port collisions. The multi-agent orchestration successfully generates contextual domain maps, but its rigid local execution model introduces significant friction for standard enterprise workflows. The friction extends well beyond local port conflicts. This line chart demonstrates the underlying economics. Because the file analyzer agent must process every significant file, the financial cost scales aggressively with the size of the repository. In practice, analyzing a 350-file monorepo takes nearly 30 minutes. Executing that single analysis can instantly consume up to 40% of an organization's daily AI provider quota. The system also suffers from severe cross-platform fragility. It relies on specific LLM tool calling capabilities that are completely unstandardized across the fragmented AI assistant market. Within the open code ecosystem, for example, the absence of a specific task tool abstraction causes phases 2 through 6 of the pipeline to silently abort, leaving the user with a useless 14. The most severe flaw is an opaque permission model lacking a config.json manifest, leaving developers blind to what the agent intends to execute. This opacity is compounded by supply chain risks. The package utilizes unpinned NPM dependencies. If a malicious actor compromises a downstream library, that altered code could be pulled directly into a local developer's environment. Beyond the technical vulnerabilities, there are serious anomalies regarding the project's growth. Historical data shows the repository acquiring stars in perfectly rounded $1,000 increments on consecutive days, a statistical impossibility for organic viral adoption. Ultimately, the framework serves as a case study in the current limitations of AI infrastructure. While the project aims to bridge the gap between syntax and semantics, its exorbitant costs and critical security failures suggest that autonomous agents are not yet ready for secure, enterprise-scale engineering.